Here we are. So thank you everybody for joining. Thank you, Jeff. It's a pleasure having you here. And well, as you all know, also as you all should know, today's speaker is Jeff, and he's gonna give his first class out of three classes, which is gonna be about the hydrodynamic suspension model, physics successes and limitations. So thank you, Jeff, for accepting giving some classes during our webinars. I asked for one. You're gonna give three of them, so that's great. And people, if you have classes, you know how it works. You just have the right button, raise your hand, or open your mic, or write a question in the chat. Feel free to do whatever you want. It's a class format, so if you have questions, just ask them directly to Jeff. That being said, Jeff, please go ahead. You can start sharing your presentation on top of mine, and thank you again.
Okay, I'll do that. Let's see if I can make things work here. It's here somewhere, right?
We still see my presentation?
No, you don't see mine
Oh,
yet.
okay.
I'm still, I'm basically talking to myself. I'm saying it's here somewhere because that's it. Okay, so good morning on the and good morning in the US. Let me go to full screen here. That's not the right thing. Sorry, it'll take me a minute to get moving in the right direction. This should now be going to full screen. And bear with me while I get a pointer. When this will... It gives... Okay, annotate. Sorry, everybody. I'm just trying to... Okay, now you should be able to see a spotlight.
Yeah, perfect.
Okay, let me go back.
I mean, we also see your mouse, but in any case, so.
Right, but right now I have lost control of the now it's going. Okay, now we're moving again. Okay. Whew. Technology. Okay, so yeah, I'm Jeff Morris. For those who I have not met, I'm glad we get the chance to at least see each other online here. And so I'm going to talk about suspensions in a sort of a broad way here. So this is really intended. This first lecture is really intended as introductory and class material, effectively. Pace, if you will, so it won't necessarily cover everything. I'm glad to share the slides if anybody wants them. Right, and I'm sorry we couldn't start at the 42, but I have a class I have to teach at 11 a.m. in the U.S. Eastern time, and so I have to somehow get over to the other building to teach that by that time. So I've titled this an introduction to suspension dynamics from basic microhydrodynamics to mixture fluid mechanics. Slightly different title, but the same basic idea is that to try to bring out the primary physical ideas and then to move to the idea of trying to study the material as a whole material rather than thinking about the discrete particles so much. Okay. And so there are many sketches here in this, what I'm going to show you, that come from a book that Elizabeth Guajali and I wrote, that where the sketches were done by Sylvie Peak from Marseille. Okay, so just to begin, to make sure we're all on the same page about what we're talking about when we say suspensions, that can span a very wide range of sizes. And so here, when you consider nanoparticles that are on the order of, say, 10 nanometers, these are used in a large number of materials in the chemical engineering world. It's also representative of protein solutions, for example. And so there's many questions at that scale where surface area is a very dominant feature because you have a large amount of surface area per volume, and surface forces can play a big role. And then Brownian motion, of course, plays a significant role. But when you get up to the scale of red blood cells, which are on the order of, depending on the species, 2 to about 10 microns in their largest dimension, then you start to lose the influence of Brownian motion, but you still have the influence of surfaces being a very strong feature. Red blood cells, of course, are deformable, and I typically tend to avoid deformable objects when I think about suspension, so we won't say too much about that. But a lot of what is said here is relevant to systems of that sort. Then you get larger to the order of 100 microns in size. You get non-colloidal suspensions, and here I'm just showing one phenomenon where you actually see a suspension in a case where there's a free surface, and you can get some very interesting phenomena where particles may in fact demix. And so the issue of how the particles arrange themselves in the system is really the crucial issue, I think, in terms of trying to think about these materials relative to single phase flows. And then you get up to the point where you get to wet granular sand. So we were all just talking about the beach in the south of France. And so for those who are lucky enough to be near one, you can go and think about suspensions with wet sand if you want. But then when you get to these larger scales, issues involving inertia of the particles can tend to be an issue. And that's going to be a topic that I'll talk about in the discussion a week from today, actually. I'll say a few things about what's known about inertial suspensions, but that's a place where there's not a great deal of knowledge, and I just want to open the field and for those who are not familiar, because I think we need some new ideas, we need some energy in thinking about those type of questions to really bring fluid mechanics to the suspension world. Okay, so that's just a broad overview. And as you change scales, the one thing that is very, very characteristic is that in all cases you're talking about particles which are nearly rigid, or at least they're only deformable up to some level, immersed in a liquid, dispersed in a liquid. And that's really a crucial thing, because the liquid, relative to having a granular material, opens up many, many different possibilities in terms of the rheology of the fluid, in terms of the things that can be dispersed in the fluid, whether it's ions or polymers. And it also then mediates forces through the fluid mechanics. And what we're going to talk about today is primarily an issue of how the fluid mechanics plays a role in the problem. So just as an outline, I'm going to do this in three sections. First, just getting started, some definitions, and then talking about the fact that we're dealing with primarily low Reynolds number or Stokes flow. So we'll say a little bit about the basics of that, and then some key one-body results that really, I think, are foundational to thinking about what goes on in suspensions. But often I've found that people who work with suspensions in industrial context are often not really that familiar with this. And so it's an area of study where the basic foundations of the systems really are not as well understood as, for example, in polymers. So everyone knows that the key issue in polymers is that you have deformable long objects which extend out in space, and then when you put a flow on them, it extends. But very often, if you ask people what's the key feature of a suspension, the issue that the fact that the particle simply can't deform and therefore resists the flow is not so well known. And so I want to bring out some of those one-body ideas because they're central to having a foundation to think about the system. And then we'll look at some two-body problems and look toward many-body systems and the ideas of how do you get to a simulation that can deal with many-body systems. And since I'm talking about this in the framework of rigorous Stokes flow hydrodynamics, I'll talk about the Stokesian dynamics paradigm as one way to simulate. There are many ways now to simulate these behaviors, but this is the one that I'm going to talk about. And then I'll say some things about the bulk suspension behavior. So some things about rheology and its relationship to the structure, that is how the particles arrange themselves in space relative to one another. And then the coupling of rheology to flow, which leads to migration phenomena, which have been a sort of a central point in thinking about suspensions for the last couple of decades. Okay, so some definitions. So a suspension, as I said, I'm going to think of it for what we're talking about today as rigid particles in a Newtonian liquid, although you can simply say that a suspension is objects which have a finite deformability and don't have a surface tension. So an emulsion is different than a suspension, that you have surface tension of the objects. But a lot of the ideas carry over from one system to the other. So there's utility in this in general. Suspension dynamics, what I mean by this is trying to understand the behavior of suspensions both in equilibrium and under flow. So equilibrium, when we talk about real equilibrium, thermodynamic equilibrium, that means that you're actually asking the question for systems which have a thermal motion or a Brownian motion. And colloidal dispersions have this, and that's an important feature, but I'm really not going to talk about it much today at all. But I will bring out the influence of Brownian motion a bit. This typically addresses the fluid mechanical and the other forces at the particle scale when we talk about suspension dynamics. So for example, I have to worry about the fact that if I move a particle, it creates a flow field which interacts with other particles. But at the same time, those particles, depending on their characteristics, may have other forces between them. They may have electrostatic interactions that are associated with the ions in the fluid and things of that nature. And so ultimately, I think what the direction that suspension mechanics has gone, while we think of it in terms of rheology, that's really a question of the statistical physics of trying to understand the average behavior of many objects immersed in the flow, right? So rheology is a very difficult aspect of problem in statistical physics because we always have to consider the rate and the time dependence of the behavior. And so we're unable to simply deal with a limit like you would in equilibrium. We have to deal with a whole sweep of variables. Okay, so let's get to the basics here. So suspensions and Stokes flow, where we say that the Reynolds number is the density of the fluid and particles. I'll say they're about the same for the most part, and if there's difference, then we'll be discussing sedimentation. The characteristic velocity, the particle size. So I use A for the radius of the spherical particles, and then the viscosity mu, which I will sometimes screw up in my notes and call eta. Sorry. So, but mu is what I mean by the viscosity. Sometimes this will be eta instead. So why do we consider this to be about zero? So there's real systems where this is definitely the case. In a number of industrial systems, you have this, and you can even think of blood at the particle scale, the behavior of muds, where you have particles which are typically on the order of, say, for clays, a couple of microns or smaller as a part of the material, coatings and cement and so forth. All of these, the actual rheological properties are largely determined at low Reynolds number. So that's means that there's direct relevance. But from a theoretical perspective, understanding the behavior is made much easier by considering linearity of the fluid mechanical motion. So the Stokes flow just makes things tractable, and it captures a great deal of the key physics. And the key ideas I'm going to say that here at the bottom, I really want to emphasize. So I do want to say that the model of a suspension, where you're asking questions about how particles interact and how they they can't occupy the same space as one another, that is just the exclude volume interactions, plays really a crucial role in understanding a lot of colloidal materials, including some emulsions, the behavior, as I said, of protein solutions and so forth. So it's kind of a base model, which is at the level of sort of the hard sphere model of liquids for equilibrium systems. A somewhat broader range of forces have to be considered when you're dealing with suspensions, but the same idea that it's a foundational piece of understanding. So for those of you who might be interested in these things, swimming often of bacteria and other microorganisms often occurs at small Reynolds number, which leads to difficulties for the the creatures in figuring out how to move at that scale because they don't have inertia, which is the way that we would swim, would be using inertia. All right, so I want to say something here that if I had to say, how do I think about suspensions, these are sort of the key ideas that come to my mind. The first key idea is that particles can't deform, but the fluid can, and these two things are mixed together. Really, that's a key issue, and really trying to understand that when you seek to make a suspension flow, you're forcing the particles to move, they encounter one another, they have interactions constantly, they can't deform, but the fluid can, and under the constraints of flow, it must, right? And so how the system organizes it to do that and the bulk properties then, these typically differ quite greatly once you get to significant fractions of particles from simple fluids. And they also vary quite a lot from dry particle assemblies. We all know that sand on in a bead behaves differently than suspension of particles, which are of the same density as the fluid would behave. And so these are some key issues about thinking about the systems. When I bring it down to a level of trying to think about the theory of the systems, I think it's we missed the 42 after the hour. I'm sorry. I meant to make mention of 42 past the hour, so sorry about that. For those who are real hitchhiker fans, I know that's important to you. But so at a theoretical level, what we're doing when we say that particles can't deform is we're kinematically constraining part of the material. But when I have that object in a flow which does deform, that induces forces. That is, it creates dynamical effects. And so really the central idea of describing the behavior of the material comes down to understanding how the kinematic constraints lead to dynamical effects in the behavior. Right. So I'll try to return to that thought. Sorry, the font here is a bit small. I hope I can see it. Maybe you have a big screen, but I have a small one here. All right, so Stokes flow, we start from this is just basic equations of fluid mechanics that I think most people would be familiar with. So we have conservation of mass and momentum. So we have Navier-Stokes equations where I'm explicitly writing the body force here, the body force density. And then I will use this index notation a lot. And so the stress, sigma here, the stress in the system is written in terms of a pressure and a viscous term. And so that divergence becomes this form on the last two terms. And then in the index notation, then I can write it as the stress is equal to minus P times the identity tensor delta ij plus 2 mu times Eij. And Eij is the rate of strain tensor. So this is this crucial object in the kinematics, that it is the rate at which I'm deforming the material, but written in a symmetric form. So this is the part of the flow that's trying to tear things apart, right? So that's the rate of strain. All right, so I'm going to spend a few slides here on one particle in Stokes flow and dealing with some of the basic problems there. So if I consider the Reynolds number at the particle scale, then I can write that as UA over nu, where that's the kinematic viscosity. And you can think of that as the convective terms then divided by the viscous or diffusive terms. And so we're going to say that that's small, which effectively means that I'm saying that the kinematic viscosity becomes very large, right? So that means that the effects of momentum are diffused through the system arbitrarily fast, is one way to think of this. Of course, you can also consider that we're just saying that the particle size is small if you prefer that. But we suppose that the motion has an intrinsic time scale, then you can write this in terms of a Stokes number being small. But if both so Stokes number being small and Reynolds number being small are just two different ways to think of the problem. I tend, for suspensions, to think of the Reynolds number and the Stokes number as interchangeable, but the Stokes number then becomes a much more important issue when you start to consider the issue of inertial motion, because then you're asking what's the particle's stopping time. So we'll see in just a moment that stopping time doesn't really have any meaning in a Stokes flow. All right, so if the Reynolds number and Stokes number are small, then we can just neglect this convective inertia term. We write the Stokes equations as the incompressibility, div u equal to 0, and the divergence of the stress, which is this minus grad P plus mu del squared U, is then balanced by the minus F. But the minus F term can simply be absorbed into the hydrostatic pressure, right? I'm going to be considering motions. There's nothing I'm going to be talking about that is about hydrostatics. So I'm just going to absorb the body force into the hydrostatic pressure. And so I will consider the Stokes equations for everything I'm talking about to have this form. And we don't have to worry about about buoyancy terms unless the particles are of a different density than the fluid. All right, so the Stokes, if you look at these equations, the key observation about them is that they're linear in the independent variables, that is u and the pressure. Those four variables, 3 for the velocity and 1 for the pressure, are appearing linearly. The pressure does not actually appear in the top equation, but the top equation exists in order to be able to determine the pressure, basically. So this is the equation of state reduced to an incompressibility statement, and that gives us the ability then to determine the pressure. So we have 4 equations for 4 unknowns. But these are linear, and linearity is important. They also have no time, right? So there's no time involved in these equations. And so, in fact, in order to predict unsteady motion, unsteadiness in these equations must come from the boundary conditions. And the boundary conditions for the cases we're going to be considering are the motions of the particles. Okay, so those are the boundary conditions on the fluid mechanics. So the linearity leads to we have linearity, which leads to, in fact, instantaneity and reversibility. So let's talk about what that means. Instantaneity meaning no time in this case, basically. All right, so one thing I did want to point out, I said this before, but I'm going to repeat it again. So sometimes things that you think intuitively about motions and fluid mechanics are wrong for Stokes flow, simply because we've spent all these years living our life in a high Reynolds number world. But when you go to low Reynolds number, things are just simply different, right? And so we have to be aware of that. So let's think about this linearity. And one of the first things is that it allows superposition of solutions. So here, if I have a particle and it's undergoing a translation and a rotation, so that's shown below, although the velocity seems to have gotten turned here. That velocity of the fluid that's induced by these two motions, so little u here will be the fluid motion, big U is the motion of the particle, and omega p is its rotation. This velocity of the fluid can be determined by summing the result of the particle translating and rotating separately, and then putting them together with the associated boundary motions, right? So that's one of the consequences of linearity. I don't have a picture for instantaneity. I can hardly say the word, so that's one thing too. But so I'll just try to describe this in a bit of math. So you start with this momentum equation. You can modify it by taking the divergence, in which case you get del squared p is equal to 0, or the curl of grad p, since this is the gradient of a scalar, would be 0. So then you will get del squared u, because I can invert the order of operations, so that becomes del squared of the vorticity is equal to 0. But what these both started as is wave equations with time dependent on the right-hand side, but now because they have infinite wave speed, that goes away. Okay, so you can think of this as an infinite wave speed. That is, if I do something at a position, that information is propagated through the entire system instantaneously. Okay, so that's a key thing in thinking about Stokes flow, is that the system, every part of the system knows about what's going on in every other part to some degree at every instant. So it's not quite true, but if you look at just a moment for that raised hand, it's not quite true, but the propagation distance is quite large. So if you look at the propagation distance, it scales as the square root of nu t, and if the kinematic viscosity is very large, then at even short times I get very long distances. Yes, Abhi.
Hey, Jeff. So the instantaneity is it related to the fact that there is no inertia in the system? Or are they separate?
It's related to the fact that there is no inertia, because the entire u dot grad u is right. So you have nothing there. And then if I solve the unsteady Stokes equations, I would have to consider some time dependence. But if I take that away, what I'm saying is that information propagates infinitely rapidly relative to any other process in the system. I can simply keep taking the viscosity larger and larger in this expression, and that says that the information propagation is arbitrarily rapid through the system.
Thanks. Thank you.
All right, so, but the simple physics idea here is this, is that if I have, say I have a particle which is moving through the fluid, it's causing a flow field that's felt at long range, and we'll see at how long range. But if I stop forcing it, so if I turn off the force, if I magically can turn off the force, all the motion stops instantaneously. So if I'm forcing, fluid out here is moving. As soon as the force is turned off, everything stops. Okay. And if you want to see this in action, you get some honey, let it be cold, put something in it, and then try moving it around with a little steel ball, and then try moving it around. As soon as you stop pulling on that ball, it will stop moving. Don't waste too much honey, though. Sorry, I'm trying to move my slide forward. There we go. Okay, so there's a beautiful old movie that describes the reversibility. If you look up G.I. Taylor and reversibility of Stokes flow, you may be able to find this online. But what he did is he took this little object, this little cuvette system where he could rotate this lever at the top that you can see here. And he put a spot of dye in, and he showed that if you rotated this around, I think it was 4 times, so 4 times 360 degrees, he did this, or if you prefer 8 pi radians. And then he rotated it back, and what he showed was that up to a small amount of molecular diffusion, the dye came back to exactly the same spot. Okay, so the reversibility is shown nicely there. But this has some interesting consequences, which for those of you who may ever use chalk at a chalkboard, you might see this, an evidence of this, is that a little piece of chalk that breaks off will fall straight down the board at the same velocity. So this is evidence of this phenomenon here, which is to ask the question, if I consider a particle in Stokes flow, will it actually move toward the wall or away when it's pulled down by gravity? So it's heavier than the fluid, so gravity could be any force here, because I'm now going to reverse that. And so what you can show is that if it went toward the wall under gravity this way, if I turned that force around, it should go the other direction, away from the wall, right? And that's really quite absurd, because that's just a change of reference frame saying that I would get the opposite physics for reversing this force. So you can go through arguments that are a little bit more complicated, and that's actually in the little book that we wrote. But it shows that the only possibility is that the particle does not change its distance from the wall. Okay. All right. So that's a result of reversibility. And so I want to now move to the issue about motion about a point, which takes into consideration the idea that I can decompose velocity fields. So this is a general idea of decomposing velocity fields, but it will be important in how we think about Stokes flows. All right, so the ultimate idea is we would like to understand how to think about the motions when we immerse a particle in a fluid in terms of breaking up the behavior into the parts that are due to the different parts of the kinematics of the fluid motion. All right, so the fluid motion at a point, there's many discussions of this in different books about how to think about this. I actually like Batchelor's description is very nice for this. Is just to say that the velocity field at a position x is equal to the value at a position plus the gradient of the velocity at that position times x minus x naught, and then higher order terms. The value of this being that this Taylor series behavior description allows us then to think about writing u infinity in terms of the velocity at a point plus a linear velocity field around it. So here, omega infinity is basically the vorticity tensor. So this is the anti-symmetric tensor. And this is the symmetric or the rate of strain tensor in the flow. So for a simple shear flow, that decomposes the flow in a way which many of you may have seen, but I think is really quite remarkable when one thinks about looking at this flow field, it's like equal parts of a rotation, solid body rotation. So that varies linearly from the origin. That is the radius. As you move out in radius, your velocity increases linearly. So you solid body motion. So this little square would rotate without change of form in that motion. But then it has this part which both compresses and extends the flow without changing the axes. That is, it's just a straining motion which changes any vector in the field according to its length. Okay. And so for the case that we're thinking about, that's spheres in this flow, then the sphere can actually sit in that flow, the part of that flow that's due to the rotation, without disturbing it at all. So in the solid body motion, a spherical particle just rotates in the case where there's no torque on it and doesn't actually do anything to the flow unless there is a and we'll come back to where it might do something. If it's in a solid body motion, nothing. But the particle, the key thing that it does is it disturbs the flow because it can't deform, right? So since it can't deform, you try to strain it and it resists that. But unlike the case that's shown here, it actually is going to be for a rigid object held in this position. So here, the idea is that I just have drawn this as a Gaussian surface, if you will. It rotates in the solid body motion and it deforms in this way. But for rigid objects, they stay rigid, and that means that this has to exert forces on the surface. Okay,
Jeff,
okay.
one question. So,
Yes.
like naively, I will assume that when, for example, a larger object tries to rotate, and it's not perfectly spherical, there will be some resistance due to viscosity of the liquid. So the assumption that it's simply a rotation, not like influenced by the fluid flow, where is it valid? Like,
So if suppose I took a beaker, go to the laboratory, take a vessel full of liquid, put down an object in that liquid, and rotate the entire thing as a solid body, the body moves at the same rate as the solid body motion. So solid body motion is really, but it plays a role because that is part of the kinematics of the motion for linear flow. Okay? So that's the point that I'm trying to make here, is that the part of the motion which actually is where a particle is disturbing the flow in this flow is all due to this. All due to the straining, none due to the rotation. Unless I exert a torque and the particle can't rotate in that flow, then it disturbs the flow.
yeah, I understand that the torque, unless you introduce the torque, that point is not here. But what I was trying to understand naively is, let's say there is a complicated shape particle, and it's like a high viscous fluid. So when the particle tries to rotate, the viscous fluid will try to resist that rotation, right? Because it's not zero viscosity. So what I was thinking, that when the particle tries to rotate, there is a reaction from the fluid as well. Not only the fluid, the particle is influencing the fluid, but the fluid is also trying to resist in some way the motion of the particle. So
I think all you're saying is that for a complicated shape is that the torque is a complicated question. But in any case, if this object tries to move relative to the surrounding imposed motion, it will have a torque on it. It must have a torque on it. We'll come back to that in a minute. Let me come back to that in a minute in terms of the Faxane laws. Right? Yes, another question?
So I actually wanted to ask, will this summation remains valid if it isn't a Stokes flow? Let's say if there is a finite inertia, can this shear flow still be represented as a sum of rotation plus this extension and compression?
Yes. Kinematically, simple shear flow doesn't it doesn't matter. It's just a kinematic statement that that's the case, right? What I can do because of Stokes law is I can superimpose the motions induced by the particle due to the interactions with both, which I could not do in a finite Reynolds number flow. So that's it. But the issue of the breakdown of the kinematics of the simple shear flow, forget about the particle here. That simple shear flow can be written as the solid body rotation plus the straining motion.
Yeah. Okay. Thank you so much. Thank you.
Okay, so let's just talk about these couple of basic cases. One is a sphere in a uniform flow, and then a particle in a straining flow. So if I have a sphere in a uniform flow, that means that I have this picture on the left where there's u infinity passing by this object that's fixed. It turns out to be easier because the boundary conditions off at infinity are homogeneous to write it as the particle is moving with a velocity minus u infinity. So get in this reference frame, and then say that, so that says that the disturbance velocity at the surface of the particle is minus u infinity. And then u and p both must decay as you go to infinity. That is, the disturbance flow, the disturbance pressure that's associated with that flow must go to zero at infinity. So the disturbance problems are much easier to solve in the usual way because they're homogeneous at infinity and you apply a boundary condition on the body. Okay, so there are many ways to solve these problems. There are linear PDEs. There's lots of ways in terms of separation of variables and dealing with the harmonics. But I want to construct the solution because I think it brings out a little bit of physics here. So the disturbance pressure must be a scalar that has to be harmonic, because if I take the Stokes equations, del squared P is equal to 0. So it has to be a harmonic pressure. And if it weren't for the fact that this particle were moving with u infinity, there would be no problem to solve. So the pressure itself must be linear in that driving force of minus u infinity. And it turns out there's only one candidate for this that satisfies the harmonics and linearity here that gives me a scalar back. And that is to say it's equal to u infinity dot x divided by r cubed. So x here is the vector from the surface of the particle, so it's r times some function of angle. And so this decays as 1 over r squared. So that's an immediate result that we understand from this problem. The velocity has two parts because it's a Stokes flow where I have del squared u is equal to grad p with a viscosity hanging around. And that viscosity comes in the particular solution, because the particular solution, if I can write the pressure, I can always write the particular solution. So you can go and play with Stokes equations and show this is true, is that if p is a known function, then the particular solution for the Stokes equations is p divided by twice the viscosity times the vector x. That is, x being the distance from the vector from the origin of your coordinate system. So the whole solution then is equal to, oh, sorry, I have to construct the homogeneous solution for it. Sorry about that. So the homogeneous velocity, there are two ways to get a velocity that's linear in u. So it must be linear in u. It must be a vector harmonic function, right? So that is that I can have u infinity divided by 1 over r, which is a harmonic function. And then I can have this second rank tensor harmonic, which is the unit vector divided by r cubed minus 3xx over r to the 5th times u infinity. Okay, and then the a cubed comes out here for reasons that this ends up giving us the right dimensional form. So in order to determine all those coefficients, I think I had 3 of them. Yes, I have 3 of them. Then I have to apply the continuity and the boundary conditions. So this requires some work, and you can find the coefficients. But in the end, what I want to focus on is that the velocity has a dominant piece, which goes as 1 over r squared, 1 over r, sorry, delta ij over r. And then I have this xi xj over r cubed. All of these are 1 over r. The pressure decays as 1 over r squared. And so the velocity field decays very, very slowly, 1 over r. And the stress field decays as r to the minus 2, both for the pressure and for the viscous stress that goes as the derivative of r to the minus 1, which is r to the minus 2. Right, so these are results which are crucial in terms of being able to rationalize the forces and torques and stresslets on the body. We'll come to what the stresslet is in a moment. So that flow field is not a very good picture, but the picture you can see here is that if I'm in the frame of reference with the particle is fixed, then the flow goes by and is disturbed. But if you actually get in the frame of reference of the particle, then the disturbance flow actually looks like this. And it's actually twice as strong along this axis as it is along this axis. So you can take those solutions, play with them, do some MATLAB plots, which is what these are, to get some pictures. All right, so one of the key issues that one has to think about is the drag on a particle in a flow. And so the drag in Stokes flow is, there's a classic well-known result of that it's 6 pi mu times the particle size times the driving velocity u infinity that would be passing it. And this can be written in terms of what I'll call a resistance function. So I'm going to now introduce some notation where the resistance of the body, that is giving a force associated with velocity. So this is a notation that John Brady and George Bossis developed in setup of the of Stokesian dynamics. So you'll find this in the book by him and Carilla, if you're interested in this, having different notation, but this is the form that's used in the Stokesian dynamics paradigm. So there's a resistance due to of the particle to velocity inducing a force, and that can be written as u particle minus u infinity with a minus sign out here. So then if the particle is not moving, that just becomes RFU dot u infinity, and RFU then for a sphere has this particular form where it's the identity tensor with the relevant quantities in front to give me back that Stokes drag law. All right, so I'm not going to go through the calculations of the drag. I'm just going to say that if you want to do this, it's easiest to perform doing an integral off at infinity. So you consider that you have a particle immersed in fluid like this, where the outward pointing vector and out is shown like this, and then I have a volume like this with S infinity out here. So this is set up so that I can use the divergence theorem. And so what the divergence theorem tells us is that the divergence, that the stress dotted into the normal, which is the traction vector at the surface, and this gives us then the drag on the particle. So that's the drag right there, as we show at the top up here, with a minus sign. So that's actually the negative, because N out is this direction. And if I actually want the force on the particle, I need the normal that points out of the particle. So a detail. But at any rate, since the divergence of the stress for Stokes flow is equal to 0, then the volume integral goes away. And so I can write this hydrodynamic force either in terms of sigma dot n over the surface of the particle, or I can go off to infinity and write it as the integral of sigma dot n ds. And since the integral ds gives us something scaling as r squared, the only way that I can get a force that's finite, independent of how big I take the system, is to consider the stress pieces that are going as r to the minus 2. So I only have to consider the dominant pieces in the stress to actually do the computation. And I can tell you it makes the calculation enormously easier to do that. All right, so so that's one key problem. Another key problem, and it really is even more critical for rheology, is to think about what does a particle do in a straining flow. So if I put a particle down in a straining flow, it's going to disturb that flow and induce a pressure. And the flow I'm talking about is E dot X. So that's this flow here, right? So that's the flow of this straining motion around a particle. So it turns out, I want to point this out, that since this particle, a sphere, can rotate in this flow without disturbing it at all in the solid body motion, the disturbance flow caused here is the disturbance flow caused by this motion. So when I get the disturbance from this, I can sum it with this velocity to get the overall velocity field induced for the interaction of a particle with a shear flow. Okay, so now I'm solving the problem since it's since it's a disturbance flow with the disturbance velocity is equal to the undisturbed flow on the surface of the particle, and then the velocity and the pressure field off at infinity are zero. So I'm saying the particle is disturbing this straining flow at its surface, and then the flow field decays away. Right, so to get a scalar harmonic that's linear in the rate of strain is what we now have to do to construct a solution. So we constructed a solution before. So the scalar harmonic for the pressure is EIJ dot delta J, and then the XI XJ term. These then have this dependence as R to the minus 3 for the pressure. Okay, so delta IJ, EIJ turns out to be the trace of the rate of strain, and the trace of the rate of strain is the same as the divergence of the velocity. So the pressure, it turns out, can be written more simply just this way because the incompressibility gets rid of this first term. We can write the particular solution again by taking the pressure divided by 2 mu times x, and so it has this xxx times EIJ form. And the homogeneous solution is this complicated object, which involves 3 different ways to get a velocity from the rate of strain dotted into the position vectors. Okay, so we can solve this, and then the key physical point is the velocity decays as 1/r squared, and the pressure decays 1 order faster because it must be the equivalent to the gradient of the velocity, because they both enter the pressure and the gradient of the velocity into the stress. So the pressure decays as R to the minus 3. Okay, and so that flow, sorry, this got cut off a little bit. That flow field, if I had a particle immersed in this, you see the streamlines. But a kind of remarkable fact is that if I put a sphere down in a simple shear flow, it induces closed streamlines off to infinity. So when I take the sum of the disturbance from here and add it to the simple shear flow, looked at from the side, it looks like this top little picture, like an eye, and the envelope of these closed streamlines actually extends off to infinity. And that has influence on the behavior of particles that interact in the flow. Okay, so the quantity that one can obtain from the flow past a sphere was the drag force, but the quantity that one can obtain from immersing a particle in a straining flow that's crucial is the stresslet. Okay, so the stresslet is that little bit of stress that's induced in the system by the particle. And so we have to think about this in terms of moments of this traction distribution. So the drag is summing up all of the force on the surface of the particle, all the traction. And so that's the 0th moment. The first moment of that surface traction distribution around the surface can be written this way, so that I take sigma, sigma dot n is the traction vector locally on the surface of the particle. And then I take a moment of the position vector x of that traction. So I get 2 parts. If I take the symmetric part, where I take mij plus mji and divide by 2, I get the stresslet. And if I take the anti-symmetric part, I get mij minus mji, and that basically is then going to give me back the torque. Okay, so the stresslet is the symmetric thing which is equivalent to the torque. So for those who aren't familiar with the stresslet, you simply, it can be quite difficult to think about, because the stresslet doesn't enter into either a linear equation of motion, an equation of motion for the linear momentum, nor does it enter into the equation of motion for a body, where it is we're asking what its rotational motion is. That's the torque that enters there. However, the stresslet is sort of a crucial object because it's telling the influence of the surface tractions on the motion that I'm trying to impose. So I'm trying to impose a straining flow. The surface is resisting this, and this is telling me by how much is it resisting that. Okay, so that's the basic idea of the stresslet. All right, so here the calculation of the stresslet is a tedious thing, right? The torque is even worse, right? So I chose not to put those in because they're really a big mess to calculate. But I did want to indicate that it's simplest to determine the stresslet if you want to take the velocity of the pressure field and determine it by using this far field idea of carrying your calculation off to a surface at infinity. And so you find that the stresslet is 20 pi over 3, some number out in front, depends on the viscosity, but critically it depends on the particle size cubed. Right? Depends on the particle size, the diameter cubed. Right? So it's a volumetric object. Yes.
So Jeff, naively, I'll assume that the antisymmetric part, Aij, will be 0 for spherical shape. Is that correct?
In this flow, it would be 0. Yes, that's correct. In this flow, that would be correct.
Okay,
That's
okay,
right.
okay.
Yeah.
And so like physically, how to think about that antisymmetric part? Is it primarily the property of the object, how the shape of the object is, or it has to do with the flow as well?
Well, the shape of the object will affect the exact issue, but it's really more to do with the flow. And I would say that the best way to think about it is to think about what are the forces that this flow is inducing on this object. So along this axis, the forces are pushing out on the fluid. There's an outward pointing force here and an outward pointing force here, if I reduce it to its elements. And along this axis, there's an inward pointing force. So think of it that way, that I have 2 inward pointing forces and 2 outward pointing forces. So that's the structure of that dipole, force dipole. And so what it does is it induces a velocity which is in the opposing direction of this. If I have a force which is pulling in along this axis and pushing out along that axis, the net motion is in this direction. Right? So if you draw that picture of what does the force look like in each quadrant, then you can get the idea of this. And along this axis, it's easiest to think of it perhaps as that it's a force that's pushing back here, pushing down here. And so it has that dipolar structure along this axis and a dipolar structure of this direction along the other axis.
But this
that's
information can be captured by the symmetric like the symmetric component of the Mij, right? Because I don't see what
That's correct.
asymmetry
That's
is
also
right.
That's
so-
all. That's
Okay.
that.
Okay.
But how if it was a very long, then what would be different is that it wouldn't have the same magnitudes of the forces in the opposing directions.
Right. That I understand. Yes. And that is what I.
But it remains a symmetric.
So like I was thinking that
It
can there.
remains a symmetric object.
Right. What I was thinking is, suppose there is a symmetric object but the flow is not uniform in the sense that the flow has.
There I have to. There we have to stop though, because what we've done is we've reduced the flow kinematically to these different forms, and we're not mixing them up. We're asking, what does it do in this flow and what does it do in this flow, right?
Okay.
So that's the decomposition is necessary to make progress with thinking about this. You must decompose the problem.
Okay, thank you.
Right, so we have the stresslet. Okay, so we have the stresslet, which can be written again in a resistance tensor form, and I just do this in order to give you 2 points. One is the basic notation comes out where I have the resistance of the body to create a stresslet induced by the rate of strain, and that can be written in terms of the particle kinematics relative to the imposed kinematics, but the particle is rigid, so its rate of strain is 0. And so this thing becomes just RSE dot E. That is, that's the form you can write for the resistance description. And so then this RSE is a fourth rank tensor, and it has this delta IK delta JL form for writing it against the, let's see, KL described EKL. Okay, so now we get to the physics that's relevant to rheology, and that's using the stresses. So Einstein's viscosity is a very famous idea, and here I'm going to give the elements of how it comes about. So the stress in a suspension is in a volume average is just the average of the stress at every point in the space. And so that can be written in the usual definition of an average over a volume here, 1 over the volume, and the integral over the volume of that quantity, sigma. So sigma for the fluid, so I can split this up into the integral over the fluid and the integral over the particles, right? So space is apportioned to particles volume and fluid volume around them. So in the particles, in the fluid, I just have the pressure and the viscous stress. So I can take the average over the fluid of these quantities. And it turns out, since the only things that strain, this is just the average rate of strain, and the average of the pressure is the average in the fluid. But then I have this leftover piece, which is the stress inside a particle. Well, this is indeterminate if it's a rigid object, right? So if it's a rigid particle, I don't know what the stress is based upon a constitutive law. So I have to do a trick. And this trick, actually, the first place that I know of it came from the original version of Landau and Lifshitz fluid mechanics book from 1959. It's very well known from bachelor's work as well. So you say that the stress, you explode it out here in terms of a divergence of the moment of the stress minus the piece that wasn't there before, right? So you write this out, you can check this. And what you get then is that the integral of this sigma ij over the volume of the particles, then because the divergence of the stress here, so this term is the divergence of the stress, that's equal to 0. So I only have this other one where the divergence theorem allows me to write that as a surface integral. So this term is then turned into the surface integral. And that surface integral, it's actually this surface integral, when I symmetrize it, I get the stresslet. Okay, and so then that's saying that the stress inside a particle, when I multiply it by the volume of the particle, which scales as a cubed, actually gives me back the stresslet. Okay, so the average stress inside a particle is determined by the forces at the boundary in a first moment of that distribution. Okay, so then I can take this thing, and you can see that 4 pi over 3a cubed is the volume of a particle. When I recognize that the total stress is the number of particles per volume times the average stress of one particle, then I can rewrite that term as 5 times the volume fraction times the rate of strain. And so I then have the classic result that the Einstein viscosity is this part that's due to the fluid, 2 mu, and then a part that's due to the particles, the phi dependence. Okay. So one quick last thing about single body results are what are known as Faxane laws or Faxane relations. And these relate the force, torque, and stresslet to the imposed motion, u infinity, and the particle motion relative to that. Okay, and so one of the things that you have to notice is that the force and the stresslet actually involve terms that are due to the higher order variation of the flow relative to just being a linear flow. So the force has these pieces which are associated with the finite size of the body. And in particular, if del squared u is non-zero, for example, in a pipe, del squared u is the curvature of the flow field due to a pressure-driven flow, then the particle, even if it's force-free, will move with a different velocity than the surrounding fluid. Okay, so that's a finite size Faxane law result. And likewise, if you have a flow which has enough variation, that is, if it's cubic in space, that is, that the linear part has two derivatives and has a finite value at that point, then there is a change to the stresslet associated with the finite size. So this is because the body reaches out into the flow, and you have to consider then the actual finite size. So you can't simply take the velocity field that would be present at its center to get the force and the stresslet. The torque for a spherical particle, I don't have to worry about those things because the particle has the same symmetry as the essential flow. So the symmetry of a sphere and the symmetry of the streamlines means that I don't get a finite size effect for the torque on a sphere. So Fick's laws are available for some other shapes of particles as well. So I won't go into that, but that's this form. Okay, so now that's section one. How far are we gonna get here? I don't know. Okay, so if we have interacting particles, there's a key idea is that one can split these into the far field and the near field. And so the far field interactions are computed using the leading order velocity field induced by the particle. So if I have a particle here, which is falling, and there's a neighboring particle, if the forces on these are precise values, for example, their weight relative to the surrounding liquid, then that force can't be changed by this particle moving. The particles must be net force free, so the force that drives this down must be equal to the drag. So the velocity field of this particle will respond in order to that. And so both of these particles will see have a different velocity field, and in fact will fall faster if there are two of them in a gravity driven flow, for example. Okay. So that's the far field. The near field, which is typically thought of in terms of lubrication interactions, but at any rate requires, rather than considering just the leading order terms, you have to consider a more representative velocity field when they're close together. So this becomes the lubrication interactions when they're close enough together. And so for particles which are pushed along this axis, here where it says U, that should really be W in this picture. Sorry about that. But the squeeze flow, when they're pushed together, induces a force which goes as 1 over the gap size. So the gap is epsilon times the particle size A, but here then the force is going to scale in the classic way that you would have for a Stokes law, but then with epsilon to the -1. So it goes to infinity for particles which are brought together along the line of centers. And for the tangential force, that scales logarithmically with that gap size. Okay, so it's a much weaker force for moving particles this direction when they're very close together relative to moving them along the line of centers. Okay, so the ideas of taking these far field and near field to describe multiple particle motions, we can start with two particles mentally, so that's where we'll think about things first. But this can be written in either a mobility formulation or a resistance formulation. So these use the resistance or mobility tensors that I've been starting to describe. So the mobility formulation says we know the forces and the force moments on the particles. So for example, I could say that I have particles which are force and torque free, and I have to compute the motions. So that's a mobility formulation. Whereas a resistance formulation says that the particle motion is known, but the forces and force moments have to be determined. Okay, so let me give an example of this. So suppose that I have sedimentation of two particles, right? So formulation would say I know to be a simple problem because I have these in the presentation I'm showing. Let's go back to this picture.
We lost
Let's
you
say these particles
for a couple of seconds.
Okay, I see my internet said it was unstable. So suppose that I'm considering the mobility formulation of this problem, that I have two particles the same size in this orientation, and I ask, given that they're falling under their own weight, what is their motion, right? And it turns out that they actually move slightly to the side, right? And so that's not such a simple question. But then the The resistance formulation would say that I know the particle motion. So suppose I say I'm going to push them straight, force them to fall straight down, then the forces have to be determined. And that would say I would have to actually exert a force laterally in order to do that, right? So you can see how the two problems differ from one another. All right, so in general, you can write the problem in a linear form where the force is the resistance, a generalized resistance, times a hydrodynamic velocity. And this, the inverse of the resistance is the mobility, okay? And these are what are known as the grand resistance and the grand mobility when we consider the problem a little bit in more detail. We'll see that in a moment. But I want to think about this in the following way, is that the forces and the torque and the stress, these are the dynamical variables. And these are all induced by the fact that the particles have to move in a different way than the fluid. So the kinematic variables, right? And so the fact that I have kinematics, which differs from the surroundings, induces forces and force moments, right? That's the essential about this. And the thing that relates them then is the geometry of the set of bodies. And so when I say geometry, you have a sphere, that's already a complicated geometry with the possibility of separation distance to infinity, right? And then the relationship of the separation vector has to be related to the driving direction. So in of all of the bodies and distribution. So the idea of the grand resistance comes from the fact that the entire matrix that describes things at the force torque level, that is where I'm just considering linear and angular momentum, but not the straining, is that I have the resistance that gives me the force associated with velocity, the force associated with a rotation, and this is a symmetric, this whole thing flips across the axis, and then I have the torque that's associated with the rotation. So this then would be the grand resistance, and there's a mobility which can be obtained by the inversion. So the minus infinity here is a typo. It shouldn't be there. Sorry about that. Okay, and so each of these resistance matrices that are shown here, or tensors if you prefer, are determined by the geometry of all of the particles in the system in principle. But at the base level for a single body, we saw that RFU scales with the particle size linearly. The T omega term scales cubically with the size of the particle. And then these off-diagonal terms scale differently. They scale quadratic with the size of the particle. Okay. All right, so how do you use these things? So I just want to say a few words about the Stokes dynamics paradigm, because I think if one is deeply involved in thinking about the behavior of suspensions, the results that arose from Stokes dynamics analysis over, from the mid 1980s until today are crucial to thinking about the system. So the dynamics in the system is solved by a Langevin equation, where we actually then consider on timescales that we worry about, the left-hand side would be equal to 0. So we have a hydrodynamic force, I have the interparticle or external forces, and then I have the Brownian force, right? So E here is the represented all the forces that can be described by a potential, either an interparticle potential or for what potential, for example. So if there's no Brownian motion, then I can say that the forces on the particle that are force and torque free, I must have a balance between those forces which come from the external potential or the interparticle potential and the hydrodynamic pieces. So here's the hydrodynamic piece must balance with the conservative forces. Okay, that's a result of force and torque free. Okay. So the hydrodynamic force moments, the force and torque is as the translational and rotational motion. So this is a generalized form where the force and the torque. Can you hear me? Because did I go out there?
No, it's okay now. It's been
Okay.
worse. Yeah.
Up and down a little bit, right? Okay. So the velocity and the rotational velocity is embedded in this U-hat. Relative to the imposed motion can be written in terms of this resistance function, which captures both force and torque. And then I invert that and multiply it by the external force. But then it also involves this other piece, which is the forces which are induced by the particles being in proximity to one another in a straining motion. For a single sphere, this gives me nothing. But once I have two, that's not nothing anymore. Okay, and so the Stokesian dynamics paradigm is embodied by the method of how you construct the resistance here. And the resistance is actually determined by pre-solved pair problems. So we take the mobility in a far field approximation up to terms that are of order r to the -7, and then I invert that. So I get this form. I have the lubrication interactions, which are the detailed interactions that I was describing for pair particles. Because they're singular at contact, then they don't care what the surroundings say. So those are a pair problem by nature. And then I have the portion of the lubrication which is associated with the far field. And I have to subtract that off to avoid double counting. So I take the far field description and the near field description, I sum them, and I get rid of the part that came from double counting. So that's the basic algorithm is near field plus far field, subtract out the double counting. Okay, and that algorithm is used in other systems as well. This basic paradigm of understanding the far field and the near field at pair level, and then finding a way to approximate the many-body dynamics. Okay, so one thing is that if we get rid of all external forces, we just ask what happens to a pair of particles in the flow. This equation that I had on the prior sheet here, right, reduces down because this is gone, right? There's no external forces. So it may look as though the problem will be boring, but in fact it becomes fascinating because it says that the velocity relative to the surrounding motion that is imposed, so if I have a simple shear flow, then this RFE double dot into the rate of strain induces a force. The particles must be force and torque free, so they must move. This is the mobility multiplied by that. And what this leads to is the motion of a second particle around a first then becomes this rather complicated structure. That is, I'm sitting on one particle, the other particle will then move around me, but both are symmetric. So it really is a motion that looks like this. Okay. All right, so we have these closed trajectories which actually go off to infinity. I have only about 5 minutes and I have too many slides to get through. So we may have to take up the rest of this at the beginning of the next week. So, all right, so we had this was our original motivating picture. And so I want to then say a little bit about bulk suspensions. In particular, for bulk suspensions, there's a rule of thumb that if the particles are less than about a micron, they're Brownian. And if they're greater than about a micron, you forget about Brownian motion. Of course, you have to worry about that transition zone. And so here, there's some typical values. So in water at room temperature for a rate of strain shear rate of just 1 reciprocal second, then this Peclet number is let's see, I have this for 5 microns. It's quite large. Peclet number here is the dimensionless shear rate normalized by the thermal motion, right? So it's telling me how far am I from equilibrium. So if the Peclet number is 0, particles move only by Brownian motion, I'm at equilibrium. As I shear the system, the Peclet number increases and I'm moving away from equilibrium. So once I'm up at hundreds in the Peclet number, shearing motion dominates over the Peclet number, the Brownian motion effect, sorry. Okay, so for particles that are 5 micron, the particle Reynolds number at this shear rate in water is about 1/2, which says I shouldn't forget about inertia. So we'll talk about that a week from today. I'll say some things about that. but the Peclet number is about 600. As the particles go below a micron, you can see this number becomes very small at this shear rate, and that means that motion is much more effective under those conditions than the shearing motion is. So the system is just disturbed slightly from equilibrium by a shear rate of 1 reciprocal second at this particular size, so 50 nanometers. All right, so if you increase the viscosity of the fluid, however, for glycerin, this drops off at the same rate of strain for the 5 micron particle to 10 to the minus 4. And so that means that for very viscous fluids, you can easily forget about the inertia, and then the Peclet number goes up radically, meaning the Brownian motion is much less effective. Okay, so the relationship of the microscopic basis to the microscopic structure and the forces to the material properties is a key idea. So we've been talking about resistance to deformation by isolated particles that through the Einstein viscosity increase the viscous resistance. And then when you put in multiple particles, resistance to relative at contact, that's station. And those two things together can give you the idea that I get an increase of viscosity at low concentrations of the particles, and that I get a divergence at high concentration, at some high concentration. So they provide a hydrodynamic basis for the viscosity divergence. And so that occurs at about 60 to 65%. But there's a, this set of data that goes back to 1965 by Thomas, where he put together a lot of results from nearly monodisperse suspensions, as neutrally buoyant as possible in many cases, and found the relative viscosity as a function of volume fraction didn't obey one curve. It was all over the place, right? And it says that something is missing. And so that's something I want to talk about next time, is the behavior under these conditions where we have this sort of range of variability. Okay, so I'm going to close at this point just because that's a good place to transition to asking the question, what is the fuller answer to this when hydrodynamics is not a complete answer? And so let me stop at that point. I'm going to have to just take questions for a brief period, and then I have to go to my class.
Thank you, Jeff. I think that's a great ending, actually, because that leaves us with some open questions ready for your next class, so next Tuesday. So people, if you have questions, okay, can you read the chat, Jeff? Otherwise, I will read you the question.
From Harshit Joshi here, how will the viscosity of the suspension G-force on each particle along with an imposed background shear flow? I would change. Okay, so not well known what the answer to that is, and I think it depends upon how it's done, but I'll say a couple things. One is if the particles are.
Whoop, we totally missed Jeff now.
Oh yeah.
Let me come back.
Oh, Jeff.
Back.
He's back. The mic is not on, and we cannot hear you, Jeff.
And now?
Now, yeah, yes.
Yes. Kinda.
Yes. Right. So if all the particles are under a body force, and so let's just consider the case that they're dilute enough that they're all settling, then they're all inducing velocity fields which interact with other particles. So there is an added stresslet that may be induced by that. But in fact, I would say that the question is not well resolved. There's been work at Nice in the group of Elizabeth Lemaire where they've actually looked at the question of particles that were under gravity force and being sheared, and trying to understand it in terms of the flow modeling of that situation. So I would say that, and then I will also comment that Martin Maxey has done work on examining that question by simulation methods, because it also affects the organization of the particles. So all that to say, the question is a bit open, but the thought process has come down to those sort of things, and so there is a little bit of work in that. Yes. So Abhi.
Hey Jeff, this was a great lecture. So a lot of the thought that we talked about was for rigid particles. How would we think about this problem for deformable particles in terms of resistance matrix and Stokesian dynamics framework?
Say again, a lot of it was about
Rigid particles, non-deformable particles, right?
Yep.
If I want to carry over this formulation, for example, to emulsion or something else, how much of the hydrodynamics needs to be redone?
Well, I mean, so the difficulty is with an emulsion is that the particles are deformable, and so then I lose linearity in the surface is no longer the fluid mechanics is still linear in the fluid. There's a linearity, but the surfaces are deforming, so that's an intrinsic nonlinearity. So that's one issue. So what I would say is that a lot of the physics carries over, but the ability to compute things becomes much more difficult. And so then I think the issue comes down to understanding how to approximate the things which make a particle that's deformable really different from a non-deformable particle. One of the issues that's crucial to this system, and there's some nice work that Mike Lowenberg and John Hinch did back in the 90s, was to show how the deformable particles have a much they can get past each other rather readily. And this goes back to a body of work that Gary Leal and others have done to try to understand that close interaction and the flattening of the surfaces. And so I would say that there are different ways to think about that. One is simply to ask the question, if you allow the particles to be slightly deformable, is there a way to do a simplified analysis of the problem? There was a point to that. Right. Okay, but so one of the things that I think that I would like to say to everyone is that usually what happens when particles are deformable is things become easier to flow, right? And we can all be grateful for that, because our blood flows at concentrations where it would be very easy under slight variations of its concentration for the viscosity to change by an order of magnitude. Thank goodness it doesn't, right? If it did, that would be a radical problem for every one of us. And so just a thought about that is understanding why things are easy to flow is as important a problem as understanding the singular behavior that one sees at jamming of the system. And I say that because I spent years avoiding blood flow because I found it kind of boring, right? Rheologically, blood flow is rather boring, but at a biological level, that's a kind of a crucial question. So when things avoid behavior that reasonably close models have, then that's a crucial thing to think about. So that's something that I avoided, but I would say maybe others should learn from my mistake, because if you can understand these things, there's a great deal of value in that. And when you think about blood flow, one of the things that's important there is that when the particles lose that deformability, when they're malarial or when you have sickle cell, terrible things can happen to the person who has that. And so understanding those issues is one of the pieces of the puzzle to try and understand these things. And people with our, the background that the group of people who are here have some ability to address these questions. So I think it's a place where the interaction of multiphase fluid mechanics with human health is significant. And so hopefully somebody will help solve some of the problems.
Thanks so much. Thank you.
Do it before I have any of these problems, please. Hurry.
Thank you, Jeff,
Right,
for
I
your
have to- I have
answer.
to get
I think it's time to let you go. People, if you have more questions, write them down. We'll be here on Tuesday. And
Tuesday.
so, yeah. Thank you again, Jeff.
Okay.
Thank you everybody for
Thanks
being
a lot.
here.
Thanks.
Bye-bye.
Yep.
Thank you, Jeff.
Bye-bye.
Bye.
Bye.